So first we will see how to define one neural network in Python, right? So neural networks can be constructed with .nn package. So basically nn.module, this class contains all the layers that you can have. So as I was mentioning that using Pytorch block-wise or module-wise, you can define your networks, your models, DNN models very efficiently. So nn.module has all the layers predefined functions as a wrapper function, and you can use them. You can inherit this class, you can define your own class, and you can extend these functions to define your own customized layers for your DNN models. So what are the steps you remember? So this is where you will pass your input with a forward pass. So forward pass basically from the input to your output of the neural network, and backward pass is essentially when you want to compute the gradient and you want to update the parameters. Okay, so forward pass is very simple because these are just the sequence of layers, and backward pass is essentially computing the gradients with the back propagation algorithm. And that is the most complex operation, but it will be you will see that to define one backward function is the easiest thing you can do in Pytorch. So how to define one network class? So here first we need to import the packages. So basically nn.nn package we have imported as nn, and then we need to define the class for our network module. Now class net here is the DNN model that we want to define. You can rename it any model, let's say whatever model you are targeting, you can rename it from net to anything. So nn.module, these are the basic Python structure for inheriting one class. So nn.module is the superclass of this net class that we are defining here. And then we want to initialize, or we want to initialize the class itself. And for that, you need to first initialize the superclass, and then in the initializer of this class, we will create the layers for our network model. So what are the layers we need for defining our model that will be initialized or that will be defined is this in this initializer for this class. And as you can see, these are just the regular expressions and regular definition for initializer of a class in Python. We will not go into details of description of these statements. And then another function you need to define the feed forward function, which is the forward pass that we are talking about. So how the input will flow from input to output. Remember here, one thing we talked about, the computational graph. So computational graph, you have the input tensors as, let's say, we have seen x and output tensor as y, and you have your weight parameters as w and bias as b, and intermediate tensor outputs, okay, which were the a. So you just see the computational graph here. So x, w, b, a, y. So all these are essentially values that you need to store inside your GPU. So if you're working with GPU, so you need to be aware of the sizes of these tensors that you are working, as well as when you do the backpropagation, you will compute the gradients of these parameters. And these gradients also you need to store inside the GPU. So when you have very large computational graph, then you can imagine how much data that you need to store inside your GPU. And if you are out of the storage that is available for your GPU, then you will get one error, and you need to change certain parameters to be compatible for the training of this neural. So that we will discuss shortly, but let's get on with defining this forward pass that we are talking about. and you don't need to define one backward function in Python, because as I was mentioning that it's just one line of code which will define the entire backward function. So as use case example, we will define this network model, which is a LINET architecture, which takes one input and it goes through several layers. So all these layers, as you can see, convolutional layers first, then subsampling layer, which is essentially max pooling layer. Then you have convolutions again, subsampling again, and two fully connected layer. And in the end, you have one fully connected final layer with these quotient connections. So this is the entire network architecture or network model that we want to define as the forward pass. So basically, input will go from this left side to your right side at the output, and that is one forward pass that we want to define as the feed-forward neuron. Now, while defining these networks, we need to be aware of the dimensions of each layer, as you can see here, right? So these dimensions are essentially very, very important to be able to define the tensor sizes particularly. And if you are not compatible with the sequence of dimensions that you want to define, then you will get one error. So we'll talk about this. Let's get on with the first definition. So as you can see here, first we will define the initializer with all the layers definition inside this initializer. Then in the function of feed forward function, which will be defined. So all the things we are defining in this class name, which is inherited from nm.module, as you can see. So feed forward function for this definition of this function will give you the feed forward function that we will discuss, and you can have as many number of helper functions inside your network as you can. Here we have one helper function as num flat features, which is to flatten the input tensor to your one-dimensional vector. So that we will also talk. So these are the essential functions that you need to develop for defining your neural network model. So the first function that we want to define one is initializer. So in the initializer, we have first we have defined the convolutional layers. So you can you remember from the architecture diagram that you saw that we had two convolutional layers. So first we were defining the first so here we are not actually passing the input from input to output, but we are just defining the layers. And once we connect all these layers together, and then only we can actually do the feed forward pass. So while defining convolutional layer, so let's say I am defining convolution 1. So nm.conv2d, so this function is already there. Here we are just using the function to override these values with. So the dimension here first is the batch size. So first is the depth of the filter, okay, that we want to convolve with, and then the number of filters. So basically we have only one depth. So if you see this structure, so this is one input that we want to convolve with some filters here. So how many filters we are trying to convolve with? 6 filters in this convolution layer. So that is why the second dimension was 6, which is the number of output channels or maybe output filter size that we want to work with. So total 6 filters we are using here, and since we are using grayscale image, so you can represent your data in any format. And here we are talking about image format as the input data, where we are using grayscale image as the input. So it has only one channel. So that means depth is 1. So you remember from your definition of convolutional layers or convolutional neural networks, there are several layers. As you can see, convolution layer, fully connected layer. So convolution layer is the transformation from volume to volume, where you have you have depth, you have the number of filters, and the spatial features. So here, by defining this convolution 2D function, we are defining that this convolution layer will have one depth, because that is equal to the number of channels that is available inside your input image, which is grayscale image, one. Number of filters and number of output, number of feature kernel size. So here we are using 5 cross 5 square convolution kernel. So that is why 5. You can, if you have, uh, if you don't have square kernels or square convolution filters, you can define with comma and parenthesis with the dimension. So if you are using 5 cross 4 5 cross 4 convolution kernel, then you can use 5 comma 4 in a parenthesis to define your irregular convolution kernel, okay, which we don't use often. Now, second convolution layer has 6 as the input depth, and number of output depth will be 16. So 16 filters we are using here. And again, the spatial features is 5 cross 5. So as you can see here, this convolution layer output depth and this convolution layer input depth is same. So if you don't have these matching parameters, then you will actually cannot define these layers or cannot define this feed-forward neural network as one pass. Then we will define the linear layers. So just remember the figure here. So 2 convolution layers that we have defined. Next, we will define the fully connected layers. So fully connected layers is flattened. So as you can see here, we have flattened the entire tensor into one dimensional tensor. Okay, so that is where we are actually using this linear function. Okay, so linear function in this NN package will actually be used to define define your flat fully connected layer or linear layer. Okay, so linear layer we have seen before also. So W into X plus B, which is the linear definition. And again, another feed-forward neural network, which has 120 into 84, and another feed-forward neural network, fully connected layer, which is 8410. So 16 into 5 into 5, how we are getting this dimension? This dimension is essentially after flattening these layers output, we are getting this dimension. So if you see the structure, so 16 into 5 into 5, which is the total number of parameters that we are having in this layer, and then we are flattening that into one dimension. So that is why we have this. So this dimension as input. So all these connections you need to be aware of while defining these layers. So once we have defined the layers, so this layers definition is done, then we can actually define the feed forward pass to using these functions. Okay, so first we will define the first layer. So first layer is essentially first the convolution layer. So feed forward is taking the input tensor as X, which is essentially the batch, okay, batch of images, batch of text, batch of audio signal, whatever you are actually transferring as the data. So mostly we do batch processing, as I was mentioning several times before. So X is the batch input, and let's say you have 16 samples inside your batch. Here 16 images. So let's say you have 16 into 1 into 32 by 32. So 16 is the number of samples you have. 1 is the number of channels inside the image, which is 1 for grayscale image. And if you are using color image, it will be 3. And let's say size of these images are 32 by 32. So X input tensor has this dimension of 16 into 1 into 3 into 3. Sorry, 32 into 30. That is the input tensor size, and that we are passing to convol 1. So convolution 1, that definition we have done in the previous slide. Okay, convolution 1. Okay, so this function we are going to pass it through this convolution function. Then we are applying one ReLU function, which is defined in this functional. So this F is nothing but the functional API of Pytorch. So while doing the demonstration, we will see the usage of this, but this is how you will define it. So f.ReLU is giving you the access to this nonlinear function that will be applied on this output tensor. And then we are applying max polytope, which is the subsampling with 2 by 2 parameter. Okay. So since all these are essentially non-parametric layers, so ReLU, max polytope, we are not defining explicitly inside the initializer. So if you want to define it, you can also define it there and use it here. So we are directly using those layers from the NN from the functional API. And so X is the output of the first layer. Now next, we want to make available this X into the next layer's input. So next layer's convolution 2 is taking this X as input. And so see here, the practice is use the same variable name all over, because this is always a sequential definition. So if you are trying to use different names for different inputs and outputs, you will for sure make a mess of the entire network while you are defining a large network. So X input, output is X. Again, X input and output is X. That's why you can define it very efficiently. So we are defining this convolution 2 and then applying the ReLU function on it, and then max polytope, another subsampling, and X is the output. And again, we are flattening this X using this view function. So view function, you remember, that is used to resize this. Now we do not know what is the batch size that we are applying to this tensor, input tensor. So depending on the number of batch sizes, you want to flatten, right? So for 16, what is the total number of, so for 16 images, what is the total number of flattened features? So convolution is transformation from volume to volume. Fully connected layer is feature to feature. So here we need to flatten the features that are output from your convolution layers. So that is why we have defined this num_flat features as one helper function, which will actually return the total size of this input tensor X, which is the output of the previous convolution layer. And we'll resize it. Then we'll give this X to your next fully connected layer. Then again ReLU function. Then again fully connected layer and ReLU function. Again fully connected layer, which is the last. And then we'll return this X. So this X I want to compute in the forward pass. So from the input tensor, you are getting this output tensor or output of this feed-forward neural net. And that is how you will define this entire set of layers. You can see this is very modular and easy to define in Python. This is the helper function that I was talking about, which is the num_flat features. It is taking the input tensor X, which is, let's say, 16 into 5 into 5 or 16, let's say, batch size. Okay. So here we are applying slicing accuracy. So X.size will give you the size, enter list of sizes. And we are ignoring the first dimension, which is the batch size, and taking all the other dimension as the list in the size and iterating through the size and multiplying. And so basically, if you have 16 into 16, 16 for batches, then 16 to 5 into 5. So ignoring 16, you are taking 16, 5, 5 into size, and then iterating through 16 into 5 into 5 and returning this number. So this is use of slices, which is very handy in defining or flattening the features. We can use dot flatten function instead of view that I have used in this to flatten the input tensor into one-dimensional tensor. But since you can see that based on the batch sizes, this view is very, very flexible more than the flatten function. Once you have defined the neural network, then what is the step? Iterate over the data set of inputs. Now, platform you will get the data. If you are working with images, Pillow, OpenCV are very, very useful to give you uh, 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 some operations which will be very, very handy to, or transformations which will be very, very handy to apply on images. If you are working with audio, you can preprocess or get some audio data with SciPy and LibRosa. If you are working with text, then you can take help of NLTK and Spacey. These two libraries are very, very useful for text processing. So first is to load in data into your memory. Which memory? If you are working with CPU, then CPU memory, and if you are working with GPU, GPU memory. And we need to convert the numpy arrays, which will be actually played as the data. So basically, if you have data already inside your disk and you are reading it as an array, and you need to convert it into a tensor, and then you can transform it to GPU to be able to access into your model, which will be run inside your GPU. So in this lecture, we will use throughout, mostly we will work with the images. So Torch Vision will be very, very handy if you are working with images to download already existing data set, and you can work with them. So work with Torch Vision importing, and then importing transforms, as transforms will be very, very important, because transforms from this package will give you very much flexibility to apply many, many transformations onto images, which will be very useful into your neural networks or DNN models that will be found. So first, how we want to load data? So first, we will load data with defining the transformations that we want to apply on the images. So believe me, if you are working with DNN models, and if you are working with any kind of data, be it images, be it text data, audio data, whatever kind of data it is, except of tuning and tuning the parameters and getting your desired accuracy and performance, you will be applying most of the time, or you can say 90% of time, transforming or pre-processing or preparing your data for your neural networks or your DNN models. So transforms will give you some predefined transforms that you can directly apply on the input tensors as the images. So basically, transforms.to tensor, we are actually transforming these images into tensors and applying some normalization. So these are the different set of transformations we are defining with this compose function. So when we will apply this transform, all these transformations will be applied one by one. You can apply any number of transformations and define any number of transformations that you can have. And normalize will take mean and standard deviation. So first argument is mean. The set of means are essentially for the channels, input channels. So if you are working with, so here we are working with C410 dataset, which is essentially color images. So 3 channels it has, and to normalize each channel for your input data, we are defining these 3 sets of mean and 3 sets of standard deviation. Then we are defining the training set. So essentially, when you are doing the forward pass, you are essentially feeding the data from your training data set inside the forward pass. So training data set to define in Pytorch, torchvision.datasets.c410, which we are using as the predefined data set, and root is the path. So here is essentially the path where you want to store the data set, and train is equal to true, so that means this is a training data set. Download is equal to true. If the data is not available in this path, then it will download automatically and apply this transform. So which is the transform? The transform that we have defined. And then we need to define the train loader, and this is the data loader definition, which is very, very important inside to define in Pytorch to be able to effectively use the data inside your train. Because mostly, if you are using GPU, you are actually running your feed forward pass and backward pass inside your GPU. So that means you want to load first data with CPU maybe, and your GPUs will run very, very fast. And to be able to feed the data with a synchronous fashion, because if you are keeping the GPUs waiting for data, then nothing is of use. So basically, you want to define your data loader efficiently so that uh, you can uh, you can supply your data to your GPUs very effectively. So train loader, torch.utils.data.data loader, we are defining this data loader here. Training set is the data that we are actually keeping or taking the data from. Batch underscore size is defining the batch size. Now here, if you want to increase the batch size, you can increase, but again, to give how much your GPU is taking and how much you are supplying to the GPUs, that is very important. So this parameter you want to tune with different numbers for your training. Shuffle equal to true. For each iteration of training, you want to feed several sets of these batches, because let's say 4 images you want to capture or take data from this training set, and you want to give it to the training model. And if you do not shuffle, that means every iteration you are giving same set of image data or whatever data you are giving. So shuffle equal to true for defining training loader is very, very important. Number of workers. Now how many number of cores you are having, that many number of workers definition is the thumb rule, but you can define as many number of workers as you can to effectively process this much of a batch size to give the data to your teams. Then loading the data, because once we have the data set ready, then you can actually so this was for training the data. If you want to test some data, so you want to load the test data as well. So say again the same transformation, and let's say test set, we are defining this test set, and this data set is having download equal to true, but training equal to false. This is not for training, and transformation is same transformations we are. And test loader is the data loader for test. So basically, we are using the data set which we have defined with the specific transformation, and then the batch size shuffle equal to false, because for the test you do not need to shuffle your images. If you want to, you can, and also you can define the number of workers depending on the configuration you have for your system. And then you want to process the input to the network. And how you want to process the network through this feed-forward function. This feed-forward function we have defined. So x equal to, first we are applying this convolution layer ReLU and this max pooling. Again, convolution ReLU max pooling, then to fully connected layer, and final fully connected layer to give output tensor. So return x is essentially feed-forward output which we want to get from. Again, remember, so x is essentially the batch data we are giving in. That means we want to compute the loss for the batches that we are giving. Okay. So computing the loss function is the next important step, and to compute the loss function, as we have seen, that you need to compute the loss depending on a set of targets that are available. And here, as you can see, we have, let's say, 10 classes, and let's say we are initializing one random tensor with 10 values. And so this is the target or ground truth. And once you have the output from your network, which is the output from the network, so this output and the target, which is the ground truth, that these two parameters will be used for computing your loss. And as you can see, NN dot lot of loss function you can see, MAC loss, cross entropy loss. So this is mean square error loss. So many loss functions you can use directly with this NN package, and you can define your loss as criterion. And then you can define the loss with this output and target, and then you can actually go towards the next section, which is to propagate the gradients back to your network's parameter, which is just the backward function. So once you have the loss calculated, then you can use this backward function which will take care of computing the gradient. And then the next or last stage of the entire training pipeline is the update of the weights, which is again very simple. So to update the weights, what kind of optimizer we are using? Optimizer, you can use this Optim library, and SGD is the stochastic gradient descent we are using. You can use Adam, Adagrad. So there are many optimizers you can use with different parameters, and then you can actually define with zero grad. Let's say to initialize all the gradients to zero, or you can actually initialize with dot zero grad function, and then you can compute the output, then loss function, and then backward function, which will compute the gradient and then the output. So then the update, which is the last step. So update is again just the one line function that you can see dot step function will do the update for all the parameters that we have defined as the parameter. So one question here remains. So basically, one epoch is essentially to scroll through all the training set for all the batches. So let's say you have 8,000 samples and batch size is 50. So basically, how many total number of iterations you have to do to train the entire set of batch or entire set of samples? That is one epoch. And let's imagine that to have this one iteration takes 30 seconds, and how many iterations that you can have to compute one epoch. And then you can compute, let's say, I want to run 3 epochs of training. So how many number of hours or how many number of seconds you can spend to train this network. So you can do this as one exercise, and we will discuss this full training as one demo in our coming class. Thank you.